All right, good morning, ladies. So, just kind of recap, or actually I'll start off with some announcements first. So I set up all the submission sites this morning for exam 4 here. So all the submission zones are set up now, so you can start uploading the extra credit and group assignments and all that stuff when you're finished with all those. So everything's all set up for tomorrow. And that's pretty much about it. So let's continue what we were talking about yesterday. So we start talking about inductance, which again is based off of Faraday's law. So again, we have two different kinds. We have the mutual inductance here. So that's this guy, which again is when I have two systems feeding off of each other. So here I have, say, system 1, which has a solenoid, so an inductor, which has N1 worth of turns, and this one's going to start a current running through it. That then has another circuit over here, which has another solenoid, which has N2 worth of coils. So again, basically what's going to happen is as the current starts to run through here, there'll be a lag in the current, which makes it a time-dependent magnetic field, which is now induced inside of this loop over here. And we know that the current is lagged over here because of the self-inductance, which we'll come back to in a second. So basically what that does is it creates a magnetic field inside of here due to our right-hand rule. That then is a time-dependent magnetic field, which means it's a time-dependent magnetic flux, which then generates a current inside of this loop. So this one is now going to start to create a current, say, going in the opposite direction due to the fact that it's trying to counteract the increasing magnetic field here. But this current then is going to create its own magnetic field, which then goes inside of this loop, which will then create another type of back EMF and a back current inside of here, which will cause this current to now ultimately be reduced and again take more time for it to charge up. So basically these two things are feeding off of each other simultaneously. Mutual inductance is used a lot in things like pacemakers. So for example, if you know somebody who has a pacemaker, if the battery is starting to get low in a pacemaker, they'll actually have you charge that pacemaker via mutual inductance. So instead of cutting the person back open and then having to charge the battery on the inside, it's a lot easier to basically put them in a magnetic coil, which then will charge up the battery with inside of the pacemaker. But anyways, what this thing says is that the number of loops in the first circuit here times the flux in the first circuit by the second circuit is then equal to the mutual inductance times then the rate of change of the currents from the second loop. Meanwhile, in the second loop, the number of coils in the second loop times the flux in the second loop from the first loop is equal to that same mutual inductance times then the rate of change of the current from the first loop. So M here, again, is what's known as mutual inductance, and it has units of henries, and this thing is only geometry dependent. So it only depends on the geometry that these two are aligned with each other. So basically, as I take and I change the geometry, so here I have one particular geometry, but if I change this around, then the geometry changes, which then changes the mutual inductance. So basically, how effective is this mutual inductance? Self-inductance, again, so let's say I'm looking at this circuit, which has our solenoid, which is also called an inductor. And that's connected to a battery, which is also connected to a resistor. Oops, here. So this is our battery EMF. So basically what happens here, again, is if I turn on my circuit so that the current first starts flying out of here, what'll happen then is, again, I'm going to get inside of each one of these different coils, you're going to create a magnetic field due to the fact that this is now has a time-dependent current going through it. That current, let's say the current is increasing, that will then cause all the different coils to create their own currents in the opposite direction, which then forces this to try to push current back in the opposite direction, which means the overall current's going to be lagged. It's going to take time for it to charge up. So in this case, this is what's called the induced current or the back current, which then generates this back EMF, where the back EMF says if I looked at point A here and point B, I get a back EMF or potential difference between those two, which is equal to minus L, where L is what's known as the self-inductance, or we usually call that just inductance for short, times the rate of change then of the current. So what this one says then is the number of loops times the flux through those loops is equal to the self-inductance times the current. So this is where the EMF actually comes from. So just like the mutual inductance, what happens in this case then is the self-inductance only depends on geometry, just like that of the capacitor. But also notice that the potential difference then across the inductor actually goes to 0 as the inductor then goes to its maximum current. So again, if the current's running through here, I get the back EMF, so the overall current is not equal to the maximum. And actually, if I plotted it, if I plot the current versus the time, it starts off at 0 and then slowly asymptotically goes to the maximum amount of current, which is just that of the EMF divided by the resistor. So once it reaches fully charged, or if all the current is going through it, acts a maximum amount of current, what happens in that case then is that the inductor acts just like a straight wire and basically acts as if it doesn't exist. Okay? It just acts like a regular straight wire. At that time, then the potential difference between A and B is simply equal to 0, so there is no potential difference anymore since the current is at fully maximum. At which case, again, it acts just like the capacitor. So remember, if I plotted the charge versus the time for the capacitor as I was charging it up, it asymptotically approached that of the maximum amount of charge. Okay? So this thing has a lot of similarities between that of the parallel plate capacitors that we talked about before. So let's do an example. So this says that wants us to determine the formula for the self-inductance L of a tightly wrapped and long solenoid containing n number of turns of wire in its length of L and whose cross-sectional area is A. So let's talk about that. So let me go to the next page. So here, again, what we know is that the number of loops times the flux is equal to the self-inductance times the current, which means then that the self-inductance is simply equal to the number of loops times the flux divided by the current. So here is my inductor. So this thing has number of turns n, has a length of L to it. And what we're going to know is the flux which is going through it. So again, what we know is that since this is a solenoid, we have a magnetic field. That magnetic field then only points along the axis then of our solenoid. So this is B solenoid, which is equal to mu naught times the number of loops times the current, all divided by the length, right? Which is also equal to mu naught times little n times I, where again, little n is equal to big N divided by L. So good. So we also know that the magnetic flux is equal to what? The magnetic field, which in this case is the magnetic field of the solenoid, times the cross-sectional area. So this is the side view. So if I looked at it from the front view, this would be my cross-sectional area A. So this is my front view. Okay. Times cosine of the angle between the two. Right? Now in this case, again, what we know is that the magnetic field points along the axis, which means my magnetic field points in this direction. We know that the area is always a vector which points perpendicular to the area, which has magnitude that of the area, which means in this case, the magnetic field is parallel to that of the area, which means in this case, the angle is simply equal to 0 degrees. So the magnetic flux then is simply equal to the magnetic field of the solenoid times the cross-sectional area of the solenoid. So let's put all that into here. So this then becomes the number of loops times the magnetic field of the solenoid times the cross-sectional area, all divided by the current. Now using what we wrote down over here, then that's going to be the same thing then as the number of loops times mu naught times the number of loops times the current times the area, all divided by the current times the length. This current's the same as this current, so that's going to cancel. So finally, this becomes mu naught times n squared, which is the number of loops squared, times the area, all divided by the length. So this is part A. It's okay. Not too bad, right? So good. So now part B then says, calculate the value of the self-inductance if there are n equal to 100 turns, the length is 5 centimeters, and the cross-sectional area is 0.03 centimeters squared. Good. So here we now know that n is equal to 100. We know L is equal to, what was that again? 5 centimeters. And then we know A is equal to 0.3 centimeters squared. But again, there's 100, so that's 10 to the minus 4. So that's going to be the same thing then as 0.3 times. So there are what? 1 over 100. Let's see. So I want to put this into, sorry, not 1 over 100, just 100. How to do a conversion here. So this is in centimeters squared, and then what I want to do is put this into meters. So this is going to be meters, yeah, divided by 100 centimeters, quantity squared, centimeter squared. So that way the centimeter squareds are going to cancel. So it's going to be the same thing then as 0.3 times 10 to the minus 4 meters squared. Right? So good. So using this value, we get L then is equal to mu naught, where mu naught is 4 times pi times 10 to the minus 7 times N, which is 100 squared, times area, which is 0.3 times 10 to the minus 4 meters squared, divided by L, which is 0.05 meters. So plug in all those numbers, we find in this case then is this works out to be about 7.5 microhenries. So this is our value of our self-inductance, or just inductance.
Is mu naught a constant?
Yes. Yeah, so mu naught is equal to 4 times pi times 10 to the minus 7, and this has units of, I gotta remember, this is a Tesla meter per amp. Yeah, so this will show up tomorrow on the first page, so you don't have to worry about writing that down. So that's always going to be a constant. Yeah, so this is the magnetic equivalent of epsilon naught. Yeah, those two things are the same. Well, not the same, but they're equivalent to each other. There we go. That was okay? So not too bad. So last thing we have to talk about is, so again, all of our things that we've talked about so far points to the fact that the solenoid here, or our inductor, is again the magnetic equivalent of the parallel plate capacitor. So this is our capacitor. So these guys are equivalent. This is the electrical, or from electric, and this is the magnetic. So the inductor then is the magnetic equivalent of the capacitor, which is its electronic counterparts. So what we said before was that the point of having a capacitor inside of a circuit was to store energy. And this thing is to store energy in the form of potential energy, which is equivalent to the amount of work it does to charge this thing up. So what we said was that if I hook this thing up to a battery, what happens then is it takes work to basically put all the charge onto this guy, where again, this is going to be positively charged across here. This is positive charge. This is negative. This is going to become negatively charged. So the amount of work that it took to do this, which is equal to the potential energy to charge this thing up, was equal to 1/2 the capacitance times the potential squared. Good. Here, this is basically the same thing. So here, what's happening now is when I hook this guy up to a battery, and here's now my inductor with my self-inductance, we now know is that it's going to take work for this thing to force current to go through this inductor until this thing actually reaches maximum amount of current which is flowing through our system. So again, this is the positive side, this is the negative side, because again, if this thing is charging up, I have the induced current pushing into backward, our back current. So it's going to take work for the battery to overcome this induced back current to fully charge up this inductor. So in this case then, the potential energy, which is equal to the work that it takes to charge this thing up, is actually then equal to 1/2 the inductance times the current squared. So the energy that is stored inside of the inductor is then stored via the current, which it takes to fully charge this thing actually up. All right? So again, here, the inductor then has exactly the same role as a capacitor does, which is to store energy for later use. So this thing stores energy for later use within the current. So here, this thing stored charge, right? So this thing stored energy either via the charge or via the potential, where this thing is actually storing the energy via the current. Now here, we also defined what we call the energy density, where the energy density was the potential energy per unit volume. Oops, wrong volume, there we go. Which we wrote as 1/2 epsilon naught times the electric field squared. So here, we found is that we can also say that the energy is being stored within inside of the electric field, which is then pointing from the positive plate to the negative plate, where this is saying this is how much energy I have per unit volume. So if I went in here and I cut out a little tiny volume, so this is my volume of V, then this is the amount of energy which is stored within inside of the electric field inside of the plates. Here we can actually do the same thing. So here we can say, well, there's actually a magnetic field inside. So this is my magnetic field of the solenoid. So what's actually happening is that the energy is actually being stored within inside of the magnetic field, where again, if I cut out a little tiny volume inside of here, then this is the amount of energy which is being stored within inside of that volume. So here we can now define what's known as the magnetic energy density, which is then equal to the potential energy per volume again, which is equal to 1/2 the magnetic field squared divided by mu naught. So in this case, we're saying that the energy is stored within the magnetic field. Where here, this one is saying that the energy is stored within the electric field. But again, the point of it is that the inductor acts exactly like a capacitor. It's just the magnetic equivalent, where again, the point of having a capacitor is to store energy for later use. Here, the inductor also stores energy for later use. Here, this one is being stored by the fact it takes work to fully charge up this, because I have to do work to overcome this Coulomb potential to ensure that I put all the maximum amount of charge on here. Here, it also takes work by the battery to overcome this induced back current. So the more and more work I have to do to overcome this induced currents gets stored as the potential energy. So this is where the energy comes from for these inductors. And that's it. We are finally done. We now know everything for this exam tomorrow. So good. So, having said that, let's do a review. So, first things first, we did chapter 20. So chapter 20, we started looking at magnetic fields. So here we first looked at magnetic force. So we said the magnetic force on a wire. So this is for a straight wire. So this is for a straight wire. Is equal to, in vector form, the current times the length crossed by the external magnetic field, or magnitude-wise, this is equal to the current times the length times magnetic field times sine of the angle between the two. Okay. Where again here, the angle is the angle specifically between the magnetic field and the length vector, which points in the direction of the current. Okay. So this is then our angle theta. Okay. How we interpret the direction is right-hand rule number 2. So right-hand rule number 2 says we, number 1, point fingers in direction of L/I here. 2, curl toward B in direction of smallest angle. And then finally 3, thumb, which is at 90 degrees to our hand. points in direction of FB. Okay. So this is right-hand rule number 2. We also looked at the force on a charged particle. So for a charged particle, we said that the force is equal to Q times the velocity crossed by the external magnetic field. Or magnitude-wise, this was equal to Q times V times B times sine of the angle between the two. Where here, the angle is the angle between B and V. So this is our angle. Okay. This one is also given by right-hand rule number 2. So right-hand rule number 2, the only difference here is now instead of pointing in the direction of the current, we now put it in the direction of the velocity, and everything else stays the same. Okay. So the only thing that's different now is we're pointing our fingers in the direction of the velocity instead of the current. That's the only thing. Now here we have to be a little bit careful because we do have to know the sign of the Q. So this is technically true if Q is positive, but if Q is negative, what we have to do at that stage is step number 4, rotate by 180 degrees. Okay, so basically once we determine the direction of the force, we have to rotate it by an extra 180 degrees if it is a negative charge. So that's basically the only difference there. What else do we know? We know that the magnetic field of a wire, magnitude-wise, is equal to mu naught times the current divided by 2 pi times the radius. So this means that what? If this was my wire and it has current going in, say, this direction, this is the current, then the magnetic field at some point P, which is some radial distance R away, this is that magnetic field at that point. Okay. So R here is the distance from the center of the wire to the point. R equals distance from center of wire to the point. The direction of the magnetic field is then given by right-hand rule number 1. So right-hand rule number 1 says that step number 1, thumb in direction of the current. Number 2, fingers curl in direction of B. Okay. So here, current's going in this direction, so my fingers curl around in the direction of the magnetic field. So that means my magnetic field in this case curls in this direction. So this is B. Okay. It's okay? Good. Another thing we looked at was the force between parallel wires. Chronologically speaking, this is slightly different than we did, but that's okay. So force between parallel wires. So here what we saw was that the force on wire 1 by wire 2 magnitude is then equal to mu naught times current 1 times current 2 times the length of wire 1 divided by 2 pi d, where again d is equal to the center to center distance between the wires. So here we use the right-hand rule then to determine the direction of the force. But basically what we found was that if they were in the same direction, so if the currents were moving in exactly the same direction, this resulted in an attractive force. But if they were in opposite directions, this resulted in a repulsive force. That's okay. I believe the only other thing we looked at in this chapter was, oh yeah, velocity selectors. So 2 more things. So we also have velocity selectors. And velocity selectors come from what's known as Lorentz Force. So Lorentz Force says that the net force acting on a particle which is moving in both an electric and magnetic field is Q times the electric field plus the velocity crossed by the external magnetic field. So here, he said, is if we took parallel plate capacitors, so that the electric field is pointing in this direction, then here we crossed it by a magnetic field, so that if we took a charged particle of Q, this thing could go through with exactly the same amount of velocity as long as the velocity was equal to the ratio of the electric field to the magnetic field. We also saw the Hall effect. So what the Hall effect says was that if I have a conducting material which has a current flowing through it, so this thing has a current, say, flowing in this direction, and this has a magnetic field which is perpendicular to it, so this is the external magnetic field, then what will happen then is we're going to create a potential difference across here, which is what's known as the Hall EMF, where the Hall EMF then is equal to the velocity times the width times the magnetic field. So the width here is the distance between these. So this is the Hall effect. And then finally, the last time we looked at was a magnetic moment. So here, if I have an external magnetic field, say going in this direction, and we put a loop of wire inside of here, so this is my loop of wire, so that this thing then has a current running through it. Let's say our current is going in this direction, so this is our current I. Then in this case, we have a magnetic moment. That magnetic moment is given by right-hand rule number 3. So right-hand rule number 3 says that, 1, we curl fingers in direction of I, 2, thumb, which again is perpendicular to our hand. Points in direction of the magnetic moment mu. So in this case, as my current is going in this direction, that means my thumb is going to point that way. So that means mu in this case points off in this direction. So this is mu, okay? So what we found here is that the torque on this wire was equal to mu cross B, which means that the magnitude of the torque then is going to be the magnitude of mu times B times sine of the angle between the two. So here the angle is that angle between those 2 vectors, which means it's going to be this angle. So that's the angle of theta. And we also said that the potential energy then is equal to minus mu dotted with B, which is the same thing as minus mu times B times cosine of that same angle. Anyways, okay? Not too bad.
Right-hand rule number 3. I thought I did, but then, so if you curl your fingers that way.
Right, so here, so imagine if I'm kind of looking at it, so it's moving in this direction. So I'm curling my fingers like this, so my thumb is pointing off in that direction.
Okay.
Good. Okay. Let's go back for just a second. So one other thing I want to talk about here is if the velocity is perpendicular to the magnetic field. So let's put a little box in here. So if V is perpendicular to B, this thing undergoes uniform circular motion. In this case, what we found was that the frequency was equal to 2 pi times the mass divided by the charge times the magnetic field, which is equal to 1 over the period. This is what's called the cyclotron frequency. And then this is the magnetic field. So, right, so this magnetic field gets, oh, sorry, I got those backwards. This is the period. This is the period, and this is 1 over the frequency. Sorry. Think about my units there. Good. Sorry about that. Got those guys backwards. It's okay. So that's about it from that chapter. So now we can go to chapter 21. So chapter 21, the big thing was Faraday's law. So here we saw for Faraday's law, we saw that the induced EMF then was equal to negative the number of coils times the time-changing magnetic flux, where the magnetic flux is equal to the magnetic field times the area times cosine of the angle between the two. So meaning that if B pointed off in this direction, area points off in this direction, then the angle is the angle between those two guys. And again, negative sign here is just Lenz's law. So this is Lenz's law. So Lenz's law says that the direction of the induced magnetic field is opposite to the direction of change of the external field. Okay. Here we did a bunch of examples of that. Great. What else did we look at here? We looked at transformers. So transformers, what we said was that the potential across the primary divided by the potential across the secondary then was equal to, so what was this? The number of loops of the primary divided by the number of loops of the secondary? Is that right? Trying to remember. I think that's right. Okay. If not, I'll change that later. Good. And then what else did we look at? So after that, we looked at, oh, inductance. So we have mutual inductance. So mutual inductance is, for example, the number of loops in coil 1 times the flux through coil 1 by the second one is equal to the mutual inductance times the current in the second. And simultaneously, the number of loops in the second times the flux through the second by the first is equal to the mutual inductance times then the current from the first. And then we have self-inductance. So self-inductance then says the number of loops times the flux is equal to the self-inductance times the current. And that the back EMF is equal to minus the inductance times the change in current with respect to time. I think that was about it. Yeah. So here we talked about the number of different ways this can happen. So as far as the exam is concerned, again, here you want to pay mostly attention to motional EMF. So for example, like the extra credits, or one of the examples we looked at yesterday where you have this bent U-shaped conductor, and then this thing is being pulled, say, in this type of direction, right, with a velocity of v. So in a case like this, again, here you're looking at the effective area. So this is going to be your area. And then what's going to be happening here is that the area is going to be time dependent. So you have a time dependent area. So typically what will happen is this will be constant. This will be some length of L. And then this is changing by some V delta T. And then this guy's going to be moving at a constant velocity. So good. So let's talk about what to expect. So good. So first things first, the long problem. So yeah, the long problem. So the long problem is mostly going to deal with force on charged particles. So basically all this stuff here is going to be, say, long problem number 1. So here, is there anything from this page that might be helpful? Yeah, so this may or may not include a velocity selector. So I'll put this in part in here as a maybe portion. So maybe to long problem 1. But this will be basically long problem 1. So long problem 1 will be basically all kinds of different stuff with forces on charged particles. So using right-hand rule number 2. For example, if you think about the one that we did where it went down into the magnetic field region and curled around, first part of the question was asking, was it a positive charge or a negative charge using the right-hand rule? So things like that. And then it also used the period to figure out the magnetic field and et cetera. Okay. So basically you'll have something similar to that. Okay. So that'll be long problem number 1. Long problem number 2, as I mentioned yesterday, is going to deal with motional EMF. So basically this stuff here. So all this will be long problem number 2. Okay. So long problem number 2 here, this will also include, as we did this a lot yesterday, this stuff as well. So this will be part of long problem number 2. Because again, what we said was that, if I go back to my little pretty diagram here, as this thing is moving, that's going to induce a current inside of this loop, and then this will induce a force backwards in this direction, which we did many times yesterday, which involved us using that right-hand rule and then figuring out what this force was. So that meant that we had to go in here and pull on this thing with some sort of external force, which had to be equal to this force. So anywho, so all of that is included inside of these guys, right? So the force on straight wires. So that's also going to include the right-hand rule here as well. Okay. Good. So all that would be included in long problem number 2. Always okay? Not too bad. Good. So short answers. Let's talk about short answers. So this stuff, force between parallel wires, this will show up as a short answer question. What else? Torque, potential energy, all this kind of good stuff here with right-hand rule number 3. It will also show up as a short answer. Hall effect will also show up as a short answer. Which basically means that what? I'm trying to remember, I think transformers is a short answer. And one of these two, so I think actually self-inductance. But I'll put both of these on here. So these guys will also be a short answer type question. Notice here that also the direction of the force here, or sorry, the direction of the induced magnetic field is also given by right-hand rule number 3. Okay. So here the only difference is step number 1 is still the same. You curl your fingers in the direction of the currents, but this time now your thumb points in the direction of the induced magnetic field instead of mu. So, right, Number 1 is still the same. Number 2, now your thumb points in the direction of be induced instead of mu. Okay, that's the only difference. So those are our 3 right-hand rules. So, everyone's okay? So not too bad, not too bad. Shouldn't be too bad. Okay. This part here, oops, sorry. So the magnetic field from a straight wire was, why aren't you doing what I tell you to do? There you go. So this, would you stop doing that? It doesn't look good. There we go. So this is actually included inside of here. So this is included in this stuff down here, right? Because this was actually this plus this gave us this. So this by itself, don't worry too much about. So it's already included down here. So everyone's okay? Any questions? Anybody might have? So again, kind of brush up on your right-hand rules. So all of those will be kind of important as you go through. And yeah, it shouldn't be too bad. As I said, one long problem will be the motional EMF stuff. One will be the forces on charged particles. And then again, the motional EMF will involve forces on straight wires and et cetera. Okay. So not too bad. Oh, good. As I promised yesterday, we'll basically spend the rest of the time then going through some more group assignments. So this is the first one. So and I talk about all of these, but they're all up on Blackboard, so you can get access to them there. So the first one says that we have a conducting rod of length L equals to 2 centimeters, that's this rod, moving with a constant velocity of 15 meters per second, perpendicular to an infinitely long wire. So here's my wire, has current running in this direction, where that current is 10 amps. So my magnetic field is going around in this direction. So this thing is moving in this direction with a velocity of 15 meters per second. So I want to know, what is the EMF which is generated inside of this rod here between the two ends if the wire is 10 centimeters away? So that's what R is here. So little r here is 10 centimeters away and wants to know what is the EMF induced inside of this guy. Okay. So here you have to use the fact that the magnetic field is the magnetic field from a straight wire, which is the one I told you not to worry too much about here previously, but that's simply this guy. So this is the magnetic field which is being generated. This guy depends on that distance of R. Okay, so that's the first one. Second one has 2. So the first one says we have a conducting rod of mass 0.75 kilograms and resistance of 1 ohm is pulled in a horizontal direction across a frictionless parallel rails, distance 12 centimeters apart. So that's telling you the length of that rod by a massless string which passes over a frictionless pulley and is connected to a block which has a mass of 7 kilograms, which is in a uniform magnetic field, which is orientated vertically. So I'll draw what's happening here in a second. So it says the bar is released from rest, and it wants to know what is the terminal velocity at which this rod is going to reach. Did you guys ever talk about terminal velocities in 175? This is actually part of that extra credit assignment as well. So what is the terminal velocity? So terminal velocity is when the force is equal to 0. So basically what happens is if I took something, let's say like this paper towel, and I dropped it, what happens is I have a gravitational force pulling downward, so this thing is accelerating downward, but I live in air, which means that there is a drag force which happens on this guy as it's falling. So what happened is as this thing is falling and it's falling faster and faster and faster, the gravitational force pulling downward never changes, but the drag force, which is acting in the opposite direction, does change. It gets bigger and bigger and bigger and bigger. Right? As you know, is if you were driving down the road and you stick your arm out of the window, the faster you drive, the more your arm gets ripped out of socket, gets pulled backwards due to the fact that there's a drag force from the air. So what happens is as this thing falls, what will eventually happen is that the gravitational force down in this direction equals the drag force in this direction, which means the net force acting on the system goes to 0. when that net force goes to 0, the velocity then goes to what's called the terminal velocity, which is the fastest velocity that this thing is going to reach. Okay? So that's what this question is asking. Now here, there is no drag force, but what's happening is you get a magnetic force acting on the object in the opposite direction of its motion. So let's kind of draw what's happening here. So here is my conducting rails. So let's say here is one rail. Here is the other rail. And then these guys are connected here by, say, a wire, okay? On top of this, we then have a conducting rod. So there's my conducting rod, which has a length of L, right? So this is my length L. Attached to this, we then have a string, which then goes over a pulley. So basically I have a pulley here, and then this thing hangs straight down. So this is the top view. So if I draw a side view, so again, here's my conducting rail from the side. Here is, say, my bar sitting on top. So there's the bar. There's the string. And then somewhere around here, I have a pulley. So this thing is now hanging down here. And this is the mass M. So let's call this mass M, which is 7 kilograms. And then this has a mass little m, which is equal to 0.75 kilograms, if I remember correctly. Which I probably didn't, but that's fine. 0.75 and 7. Yay! Okay, great. So basically what's going to happen is what? This thing is going to cause this guy to start accelerating downward, which means that this thing is going to have a time-dependent velocity going off in this direction. But, so this thing is going to feel a tension being pulled in this direction, right? So this is my tension. So this is my tension force, which is going to be from this guy, which also has a tension force, and this has mg down in this direction. And this is going to accelerate in this direction. Now, eventually what will happen is as this thing keeps moving, what's going to happen is I'm going to build up this magnetic force pulling back in the opposite direction. And what will happen is eventually this velocity or this acceleration is going to equal 0, which means that this thing is going to start moving with a constant velocity, which is called the terminal velocity. So I'm going to reach eventually terminal velocity when this acceleration goes to 0. Okay. Which basically means that if I look at the sum of the forces on this block here, so if I look at the sum of the forces, say in the x direction, if I take this as my x direction, you get the tension pulling on it minus the magnetic force, then is equal to 0. So this is when it reaches terminal velocity. Reaches VT. So from here, all you want to do then is solve for that terminal velocity. Okay, so that's what this problem is saying. The next part says that we have an 8 by 8 centimeter square loop is halfway in a magnetic field perpendicular to the plane of the loop. So it says the loop's mass is 10 grams and has a resistance of 0.01 ohms. A switch is closed at t is equal to 0, causing the magnetic field to increase from 0 to 1 Tesla in 0.01 seconds. So let's draw what's going on here. So here what this says is that we have a square loop. So here's my square loop. Okay, so this is side length L and L. And then this thing is basically going to be halfway in a magnetic field. So here's my magnetic field. Okay, so I don't know, let's say a magnetic field points outward, just for fun. And on this side, there is no magnetic field, so equal to 0. So what it's saying is at t is equal to 0, we're going to turn on the magnetic field so that it increases from 0 Tesla to, how much was it? 1 Tesla. And a time frame delta t of 0.01 seconds. Okay? So this is our picture. So then it goes on to say, what is the induced current inside of the loop? So I'm going to create a current. And then it wants to know with what speed is the loop kicked away from the magnetic field. So basically what will happen is what? I'm going to create a current inside of this thing. Right? So the direction of the current is going to be, well, this thing is increasing magnetic field, so the induced magnetic field has to be in the opposite direction. So in this case, it has to be pointing into the page. So this is going to be the direction of my induced magnetic field, which means the current then has to be going in a clockwise direction. So I'm going to get a clockwise direction of induced current. That induced current then is going to create a force inside of here. So in this case, I now have the force. So in this portion, my current's going in this direction, force is outward, so my magnetic field is outward. So this is going to create a force in this direction. So this is going to be the direction of the magnetic force, which basically means that when I turn this thing on and I crank it up, this thing is going to feel a force in this direction, which means it's going to feel an acceleration in this direction, which means it's going to be kicked out of the magnetic field region. So what you're looking for then is what is the velocity that this thing has while it's being kicked out. And we're going to assume that this is equal to the maximum velocity. This is what's known as a railgun. Anybody ever heard of a railgun before? Nobody plays video games? Never use a railgun in a video game? No? Okay. Fair enough. So a railgun is basically you take cylinders or basically rings and you put them typically over a long rod, and then you create a magnetic field that changes very quickly, and that creates these very wonderful powered projectiles. So you can actually shoot rings of metal at things using basically magnetic fields by causing a magnetic field to go from 0 up to some maximum value in a very short amount of time. They're very cool. So anyways, cause a lot of destruction using these things, depending on how quickly you change that magnetic field. So good. So these are our 3 Faraday's law questions. And then I got one more for you, which is a mutual inductance one. So that gives you 4 to work on today. So this is a 120 coil. So we have a 120 turn coil solenoid here. Is coaxial. Oh, okay. So we're talking about the coil out here. So this has 120 coils and has a radius of 1.8 centimeters and a resistance of 5.3 ohms. And that thing is coaxial, which means it's on the outside of a solenoid who has 220 turns per centimeter and has a diameter of 3.2 centimeters. So that's 1.6 centimeter radius. So it's inside of this coil. So then it says the solenoid's current drops from 1.5 amps down to 0 in a time frame of 25 milliseconds. So that means that this is going to create a time-dependent magnetic flux inside of the coil, which means the coil then is going to respond by creating his own current. And what we want to know then is what is the current created inside of the coil? So this is the mutual inductance question. Okay. That was a mouthful. Well, I took up way more time than I wanted to today. Anyways, so you got about 20 minutes to kind of get a jump start on these. So kind of talk about these in some groups here. So let me stop sharing. Stop sharing. And I'll break you guys up into some rooms so you can kind of talk about these things. And yeah, I'll kind of check on you and we'll go from there. So we'll do 2 rooms. Sounds good. Boom, boom, boom.
you know?
I thought this one was going to be really easy, but I got 2 times 10 to the negative fifth.
For it, what equation did you use to find the EMF?
The mu naught current over 2 pi r.
For that one, for the top, do the mu, and then current times the velocity and the length over 2 pi r. Because for the E, it has it in there, on the part of it. And so I think we should combine it. Because when I did that, I was able to get it. It took me a minute though, because I was like, I don't know where these numbers are coming from.
Why do you put the velocity and the length on there?
Because it's part of the initial EMF equation, because the initial one is B times V times L times sine of theta. That sine of theta gets canceled out because it's just one.
Okay.
Yeah,
So you keep
motional
that V.
EMF. Yeah. So as Emma's saying, the motional EMF should just be BLV.
Okay.
Yeah. You know L, that's the length. You know V, that's the 15 meters per second. So you need B, but B comes from a straight wire, which is mu naught I over 2 pi r.
Okay.
That's right. That's right, Emma. Everybody else doing okay on it?
Yes.
Yes.
1, 2, 3, 4, 5. Did I enter that? Right? I might have just confused myself. I think I got it. 6
Okay.
point. 1, 2, 3, 4, 5, 6. I think I got the answer without multiplying 0.02 and 15 somehow. So interesting, but okay. You broke physics. I broke it.
It happens every once in a while.
All right. All right. You guys want to go on the next one?
Yeah.
Okay.
Check on the others. Hello, ladies. How are we doing?
A little bit stuck on where to start. We're doing the first one.
Oh, okay. Well, what you know is, as we talked about yesterday, if you have a motional EMF, then the EMF should be just BLV.
So this is supposed to be motional EMF.
Yeah, because the rod is moving. So, yeah.
Okay.
That's right. So the EMF then that's generated is going to be just the length times the velocity times the external magnetic field.
And that external magnetic field would be the magnetic field of the wire.
Correct. That's right. So here, B is going to be mu naught I over 2 pi r. That's right.
Mm-hmm. Okay. Because we were trying to start from, you told us to find the magnetic field of the wire. And we were like, but how am I supposed to use that? Looking at the equations, we're like, how am I finding a voltage with that?
Right. So that's where that comes from. That's right.
Okay.
Good. Yep. So here, you know L, you know V, that's just the 15 meters per second. You know the currents, you know the distance. So, yeah. So now you know everything.
So when you say like from one end to the other, do you mean like this way or this way?
So I mean, if the wire's moving like this, it's like that. Yeah.
Okay. Why wouldn't those be the same? Because they should be experiencing, since they're the same distance from the magnetic field.
Well, remember, for a wire, the magnetic field falls off as 1 over r. So the further and further you get away from the wire, the smaller the magnetic field becomes.
But from, like, if you have them stacked this way, if you're finding these 2 points.
Oh, sorry. Right. Right. That's because, remember that if it's moving in this direction, right? So the charged particles then have a velocity here. So the magnetic field, so if my current's going this way, my magnetic field is going into the page, right? So it's going at you. So my velocity is this way, my magnetic field is this way, so my thumb points in this direction. So that means that the positive charged particles are going to move this way along the wire or along that rod. The
Okay.
negative are going to move this way, so I'm going to get positive on this side, negative on this side, which will create a potential difference between those two sides.
Okay.
Okay. Does that make more sense?
Yeah.
Good. Okay. Yeah, so that's where the potential is. So there's no buildup of charge on the top part or the bottom part, just on the two sides. You don't look very convinced about that, but
I'm just like copying down the equation at the same time. I am listening though.
good.
That makes sense. But like if it was stationary, then the difference between the top and the bottom would be more important.
Well, if it was stationary, then nothing would happen.
Right.
So
For some reason, I'm recalling like an example or another group one that we did the difference between the magnetic field at the top and the bottom. And I think that's what got me confused.
oh, right. Well, that was just talking about the force on the wire, because there was a loop of wire which had current running around it, and that was near another wire, so that was generating a force on this one and a force on this one due to the current running through it. That's right.
Okay.
So yeah, so that's a slightly different type question. Yeah. All right, looks like the other group has a question. I'll be right back. Okay. Hello there.
Hello. Hi.
So what's going on?
Yeah, we're on the second Faraday's.
Okay.
Yeah, we just really don't know where to like plug in, like what we're like force of tension minus force of magnetic field equals 0, and we're supposed to solve for terminal, but we don't know where to go from there.
Okay, so let's take a look. So let's write all that down. So let me, here, I'll share my stuff with you, because I'm nice like that, so I'll share. Okay, so that's right. So what we have here then is that the tension is equal to, so as long as the acceleration here is equal to 0, that means if I look at this part, if the acceleration is equal to 0, that means the tension then has to be equal to the weight, right? You okay with that part?
Mm-hmm.
Go back to 175 there for a second. Flashbacks. Okay.
How do
So
we
from
know
this,
that we-
what's that?
how are we just making that assumption?
No, that comes from the sum of the forces, right? So here, if the acceleration is equal to 0, that means that the
No.
sum of the forces is equal to 0.
I meant because does it say that the acceleration is 0, or
Well,
we
that's
just,
the definition of terminal velocity. So it has to have 0 acceleration for terminal velocity.
okay?
That is my daughter screaming her head off. Okay. So anyways. Good. So if it's at terminal velocity, that means the acceleration of the system has to be 0, which means this has to be 0, which means that the sum of the forces here in the y direction also have to be 0, which means the tension then has to be equal to mg. Okay. Good. So going back to here, what this means then is I get mg minus the magnetic force then must be equal to 0. A second. Okay, so solve this now for FB, right? So this says that FB then is equal to simply mg. Okay? Good. So now FB, so what's FB coming from? So FB is coming from the fact that there's what? A current's running through here, and it's the force on a straight wire. So this is going to be equal to then I times L, right? Times B, and here the magnetic field is in this direction, right? So it is perpendicular to the current, so there's no sign, so I get I times L times B is equal to mg. Always okay so far?
Yes.
Good. Well, we also know I, by definition, is equal to what? So what am I doing here? So we know this is going to be Q times delta T, or Q divided by delta T, sorry. And we also know the length then is going to be equal to the velocity times the time. So now if I use those two things, these two are going to cancel. This is going to be the same thing then as what? Q times then the velocity times b then is equal to mg, where this is going to be the terminal velocity. Okay. Good. So finally, putting everything together, we can then say the terminal velocity then is going to be equal to mg divided by q times b. So that should be the terminal velocity.
Do we use 0.75 as that mass, or is it the?
No, this is the 7 kilogram one. Yeah. Yeah. Yeah.
So wait, we're talking about the top block, but we're using the mass for the bottom block.
Right, because the bottom block is the one that's accelerating it.
Okay.
I can't even form a question. B. I'll blurt. B. I don't know what B is. I mean, I know what B is. Like.
Oh, right. Yeah, I didn't write down what B was. Sorry about that. So let's take B as 1 Tesla.
Okay.
Yeah, one of these days I'll actually write that down, so it'll be fine.
And then the charge.
Right, so that's what I'm looking at right now. So let's see here. So there's another way we can do this, actually. Let's do this slightly differently. I changed my mind. I'm actually not going to do this. What I'm going to do instead is, let's rewrite I in terms of the motional EMF. That might make a little more sense. So we know I, so let's go back to I. So let's leave this here, but let's go back to I. So we know I is equal to the EMF divided by the resistance, right? This is motional EMF, so this is going to be the same thing as the magnetic field times the length times the velocity, then is divided by the resistance. So let's do it that way. This will make more sense. Now, since this is happening at terminal velocity, this is then going to be the terminal velocity. So let's rewrite all this stuff. So we get I, which is going to be B times L times terminal velocity divided by the resistance times the length times the magnetic field, then is going to be equal to mg. Or finally, we're going to get that B squared times L squared times terminal velocity divided by the resistance is equal to mg. Okay. So this now tells me that the terminal velocity then is equal to m times g times the resistance divided by b squared times L squared. Well, that makes more sense. Now we don't have to worry about the charge. That makes less sense there. So good. So let's take B then is equal to 1 Tesla, which means that this number is going to be slightly wrong because I don't remember what number I used to do that number. But. Okay. All right, is that okay, Adrian? Does that make a little more sense?
Yeah.
Gotcha. So here, this is just using Ohm's law, right? So Ohm's law. And then this is saying that just like you did in the last problem, since it's motional EMF, it has to be BL times B. Right? This is what Emma told you from the last problem. So now I'm just using those two things together to get this. And again, since it's specifically moving at 0 acceleration, this has to be the terminal velocity. And now just taking that and shoving it in here.
Yeah, definitely got a different answer.
Yeah, because I don't remember what I used for the magnetic field there. So what did you get for the answer?
I got 4.88 times 10 to the third.
Okay. We'll go with that then. Okay.
Hopefully it's right.
I'll check it later. It'll be fine. All right. Okay, let me go check on the other group. I'll be right back.
Reading.
Okay, how we doing?
Trying to.
On problem 2.
Gotcha. So problem 2 is, so again, here we're using the fact that the acceleration is equal to 0, right? So as long as the acceleration is equal to 0, if I look at the mass which is hanging, since the acceleration is equal to 0, that means the tension has to be equal to the weight.
Yeah, we got that, and then we set that equal to the force of the magnetic field.
Good. So that is going to be given by the magnetic force on a straight wire, right? So that's going to be I times L times B times sine and omega between the two. But here, I is going, what, through the rod. So it's going, say, at you. The magnetic field is perpendicular to that. So what's the angle between those two?
90.
90. So I get sine of 90, which is 1. So I get I times L times B then is equal to mg. Where that's going to be the 7 kilogram M, not the 0.75 kilogram. Right? Good. Now from here, you're going to use Ohm's law to then rewrite I in terms of the induced EMF and the resistance, right? So Ohm's law says that the induced EMF is equal to the current times the resistance. So therefore, the current is equal to the induced EMF divided by the resistance.
Okay, but we're not given a value for the magnetic field either.
Yeah, I forgot to give you that. So that should be like one, let's use that as 1 Tesla. Life will be great.
Okay.
Which means the number that I have written on there will be wrong because I don't remember what the actual number was that I used.
Okay.
Okay.
I was like, but we have 2 unknowns. This is a problem.
No, we'll fix that. We'll make one up. So it'll be fine.
It was like we were rereading the problem. I'm like, wait, are the rails supposed to be conducting something? Where
Well,
is
they are. They're
the
conducting current, but yeah.
Yeah. But I was like, we're given absolutely no values to do with the magnetic field or current anywhere, so I can't calculate a current. The only thing I know is the resistance is 1 ohm in the thing that's moving.
Right.
And that's it.
Sorry about that. I should give you magnetic.
Okay. I was just like, oh boy, I'm more confused than I thought if this is enough information.
In this case, no, but that's fine. So good. So now what we know is from the previous problem we just did that if you have a motional EMF, then the EMF is just BL times V.
Right.
Right. But since the acceleration is equal to 0, that means the velocity is specifically the terminal velocity in this case.
Mm-hmm.
So it's BL times V terminal. So good. So put all the pieces together and solve for VT. That's it.
So by declaring that, basically, since we're at terminal velocity, that's as big as the force of the magnetic field is going to get also.
Correct. Correct. Yeah. Yeah, what'll actually happen is if you solve this using differential equations, you'd find it actually asymptotes to that terminal velocity. So it exponentially arrives there, very similar to what we did with the RC circuits, but yeah. But since we don't do calculus or differential equations, then we're not going to do that. So we'll be fine.
Thank goodness. I barely held on in calculus. Oh, man.
So looks like we got about a minute, so I'll let you guys finish that up, and then we'll call it a day. And yeah.
Okay.
And I'll see you guys tomorrow. Well, kind of, only if you have questions. So it'll be fine.
Okay.
But good luck tomorrow. It'll be fine.
Thank you.
Thank you.
I was about to say, what the
All right, how are we doing here, ladies?
Starting on the second part, but we're not really sure.
So we use the magnetic field times the area to find the flux.
Good, so that's the flux. Good.
And then we would put that into the N times the flux equals Li and solve for current.
N times the flux.
That equal the self-inductance formula.
Well, this is not a self-inductor. No, so
Okay.
this is still, so here you're still looking for the EMF, which is created, right? So the EMF is then going to be equal to the external magnetic field. Well, let's see here. So it's going to be the flux divided by the change in time, right? So here the area then is going to be the length squared divided by 2 because it's half of that area, right? And then you're looking for the induced EMF. So the induced EMF then is going to be equal to the time rate of change of the magnetic flux. So the magnetic flux goes from half of the area down to 0 area, in a time frame of 0.01 seconds. So it's just going to be the external magnetic field, which goes from, so 1 Tesla. So it's going to be 1 Tesla times the length squared divided by 2. So that's your magnetic flux divided by the change in time, which is 0.01 seconds. So that's your induced EMF.
So 1 Tesla times 2, no, 1 Tesla times length squared over 2.
Correct.
That's because
so that is your magnetic flux.
okay.
Because it only goes in halfway.
Correct. Yeah, because it's halfway in there. That's right.
Okay.
And then you said that's divided by the change in time.
Correct, because that's your final magnetic flux. Because remember, change is final minus the initial. Your initial magnetic flux is 0.
And the
So-
change in time is 0.01.
Good. And just make sure that you put 0.08 squared instead of 8 squared, because that's in meters. So,
Okay, and that's gonna give us the current.
well, that's going to give you the EMF. So then to get the current, you use Ohm's law, which says the current then is going to be the EMF divided by the resistance.
Okay. Okay.
Everybody's okay?
I just, looking at the problem, I would not have known to like go. I don't know. I
Same.
would not have known where to go, and obviously where to go on the equation like setup.
Gotcha.
I got the answer.
Nice.
There we
I
go.
only got the answer though because you told me exactly how to plug it into my calculator.
Gotcha. Now to do part B, you're going to use the fact that it's feeling a force. So now what you're going to say is the force which is acting on it, which is the magnetic force, is then equal to the mass times the acceleration, right? Just Newton's second law. Here, the force is the force on a straight wire. So in this case, you get I times L times B, because the angle between the two is 90 degrees, so sine of 90 is simply 1. So your force then is going to be I, which is that 32 amps, times the length, where the length is only going to be the length in that one portion of the wire, which is 0.08 meters, times magnetic field, which again is going to be 1 Tesla. That then has to be equal to the mass times the acceleration. But you know the acceleration is the same thing as the change in velocity divided by the change in time. So that's going to be, goes from 0 velocity up to a maximum velocity. So your final velocity is going to be the maximum velocity minus the initial velocity, which is 0, all divided by that change in time of 0.01 seconds. Those kind of make sense? All right.
Okay.
Am I speaking too quick?
Yeah, just a little. So I got to 32 times 0.08 times 1.
Well, let me share. So here we have FB is equal to MA, right? Newton's second law.
Yes, with you.
FB is going to be I times L times B,
Okay.
and that's going to be equal to M times delta V over delta T.
And delta V over delta T.
Remember, acceleration is equal to the change in velocity divided by change in time.
Gotcha.
Good. So here, let's keep playing with the right-hand side. So the right-hand side then is going to be equal to M times the final velocity, because the change in velocity is going to be equal to the final velocity minus the initial, which was 0, all divided by the change in time. Good. So now let's solve this for the velocity. So the velocity then is going to be equal to the current times the length times the magnetic field times the change in time, all divided by the mass.
And the mass is...
Good. So it's going to be 32 times 0.08, because that's the length, times the magnetic field, which is 1, times the time, which is 0.01, divided by the mass, which was, what's mass?
10 grams.
10 grams, so it's 0.01. Good. So this 0.01 cancels this 0.01, so I don't care about that guy. 1 is just 1, so that's 32 times 0.08. So what's 32 times 0.08?
2.6.
3.6?
2.6.
2.6?
Mm-hmm.
I got 2.6.
Yeah, I got 2.56. 2.6.
2.6 meters per second.
We got double.
That was double what I wrote?
Yeah, because on the it says 1.3 meters per second.
Oh, okay. I see what I did. So let me change one thing of what I did. So here, delta V, actually another way we can write the acceleration, I think is what I actually did, was I wrote this as the average velocity divided by the change in time. So the average velocity is going to be equal to, the final velocity plus the initial velocity divided by 2. So that's where that extra factor of 2 comes from. Sorry about that. So this should be the average velocity divided by 2. Yeah, so that's where that extra division by 2 comes from. So, which gives you the 1.3. Okay, sorry about that. But anywho, good. Oh, good. So now you just got the mutual inductance one to do. So we're technically out of time. Actually, we ended about 8 minutes ago, but that's fine. So if you have any other questions tonight, just let me know. Otherwise, good luck for tomorrow. Should be good. I got one more group assignment to do, and then you can hand in all those, and life will be great.
All right, bye.
Bye, everybody.